Good morning, good afternoon, and good evening. Welcome to ISSCC2021 plenary session. The first plenary presentation is given by Dr. Mark Liu of TSMC, entitled Unleashing the Future of Innovation. Let me briefly introduce Dr. Mark Liu. Dr. Mark Liu is chairman of Taiwan Semiconductor Manufacturing Corporation Limited, TSMC. Prior to this, he was the president and co-CEO of TSMC from 2013 to 2018, where he oversaw TSMC's leading-edge technology development and was co-COO from 2012 to 2013. Before that, he served in a number of executive positions at TSMC, including Senior Vice President of the Advanced Technology Business and Senior Vice President of Operations. Dr. Liu established TSMC's first 12-inch fab and later TSMC's GigaFab operations. He also served as president of Worldwide Semiconductor Manufacturing Corporation prior to its merger with TSMC. Dr. Liu joined TSMC in 1993 as an engineering deputy director and established TSMC's first 8-inch fab. Before joining TSMC, Dr. Liu was with AT&T Bell Lab in Holmdel, New Jersey from 1987 to 1993 as a research manager for the High-Speed Electronics Research Laboratory, working on optical fiber communication systems. From 1983 to 1987, he was a process integration manager at Intel Corporation, Santa Clara, California, developing technologies for Intel microprocessors. Dr. Liu is also a chairman of the Taiwan Semiconductor Industry Association, TSIA. In addition, he served on the President CEO Advisory Board of the Massachusetts Institute of Technology and on the Engineering Advisory Board of the UC Berkeley College of Engineering. Dr. Mark Liu received BS degree in electrical engineering from National Taiwan University. He received MS and PhD degrees in electrical engineering and computer science from University of California, Berkeley. Please join me in welcoming Dr. Mark Liu.
Good morning. It is my great pleasure to join you today. Thank you, Kevin, for the very kind introduction, and the committee for inviting me to come and speak here. Before I start, I hope you and your families are all safe and healthy in this pandemic. TSMC is incredibly grateful for the many professionals and essential personnel who are working tirelessly to get us through these difficult times. We are in the midst of a global pandemic, and our technology community is also called upon to help address some of the most acute needs during this crisis. From deciphering the virus genome to contact tracing to drug discovery and vaccine development, we have witnessed the critical role that high-performance computing and mobile technologies have played in the fight against COVID-19. Today, the role of the semiconductor industry as a foundational technology is more important than ever. Over the past few decades, technology has brought a profound shift in the way we experience the world and how we live our lives. For example, more than half of the world's population, 4.66 billion to be exact, are online. There are 3.6 billion social media users, and 2.63 billion people stream videos online, and the list goes on. Today, technology is fully integrated with our lives, whether we realize it or not. Clearly, semiconductor innovation is at the heart of modern technology advancements. that are transforming our lives. Many of those innovations are first introduced as the most advanced technology nodes the industry has to offer, because advanced technology nodes offer the highest speed and the highest energy efficiency. Over the past 50 years, the most advanced technology had been available first to integrated device manufacturers, or IDMs, typically only to very special applications such as CPU. Others had to make do with technologies that were one or several generations behind. The 7nm logic technology, which started mass production in 2018, was a watershed moment in the semiconductor history. The 7nm logic technology marked the first time that the world's most advanced semiconductor technology was made available broadly to all semiconductor companies. This watershed moment led to game-changing products across a wide space of applications, including 5G, microprocessor, GPU, networking, gaming, and automotive. For example, the EPIC Gen 2 processor combines a new chip architecture with 7nm technology and delivered record-breaking energy-efficient high-performance computing for data centers. It boosted performance by more than 2 times, or allow a power reduction of 50% compared to its previous generation. Leveraging the 7nm technology, the A100 AI accelerator's performance in this system solution is improved by an astounding 20 times or more. More significantly, this innovative data center solution can substantially lower the cost of ownership with a smaller footprint and deliver much more efficient computing. Those are just a few examples. Today, TSMC 7nm technology has enabled over 150 products in the market. As of August 2020, we shipped 1 billion 7nm chips, enough silicon to cover more than 13 Manhattan city blocks. This trend of democratization of technology adoption will continue with steady progress in chip-level scaling, EUV enhancement, and a variety of device-enhancing techniques, such as high-mobility channel. Well, there may be suggestions that device technology improvements is slowing down. Our product data shows that power reduction at the same speed or speed gain at the same power and logic density are still right on track to sustain the historical trend over the past 5 generations, with 5nm being a full stride node and 3nm another full stride node. By the way, 3nm technology development is making good progress and well on our schedule. Looking ahead, industry and academia have been working closely to innovate in new transistor structures and new materials, along with new system architecture and 3D integration to sustain the technology advancement beyond 3nm. Let's take a look at some of those innovations. Lithography has traditionally been the main driver for advancements in device density. The recent innovation of EUV lithography broke through the resolution bottleneck of 193 immersion lithography. It delivers higher patterning fidelity, shortens cycle time, and reduces process complexity and defect rates. EUV is used in more than 10 mask layers at the 5nm node for line cut, contact, via, and metal line patterning. Single-layer EUV patterning replaces multiple layer of 193 immersion patterning resulting in reduced mask count and lower defect density. It may be fair to say that, with the introduction of EUV and its enhancements, lithography resolution will no longer limit device technology as it has in the past. Instead, lithography throughput and other semiconductor challenges may rise to become top issues. On the topic of EUV throughput, it is critical to offset increased power usage of EUV and reduce the total cost of patterning to a level that is comparable or even lower than quadruple patterning. A key indicator of EUV throughput is source power. There has been steady progress in EUV source power, now reaching 350 watts. This enables 5 nanometer high volume production, paves the way for 3 nanometer and 2 nanometer development, and provides a path to reducing lithography cost over time. We are also seeing some major breakthroughs in new transistor structure and new materials. Unlike earlier generations, when Dinar scaling provided the principal guideline for device performance advancement, logic technologies today utilize a variety of materials in device innovations, co-optimized with circuit designs. Shown here is the first 5 nanometer FinFET featuring high mobility channel in volume production. This innovation was built on many years of advanced research. Going forward, beyond the FinFET, Nano-sheet transistor may offer additional performance and power efficiency. On the left is a TEM picture of a Nano-sheet transistor with tight space between sheets to reduce parasitic capacitance. This Nano-sheet transistor achieves smaller drain-induced barrier lowering and subthreshold swing to boost circuit performance as compared to previous technology generations. Transistor performance improvement translate directly into lower VDD operation of SRAM. The Shimoot plot shows fully functional SRAM at 0.46 volt. In the past few technology generations, design technology co-optimization, or DTCO, combined with intrinsic scaling was adopted to achieve the desired logic density and die cost reduction. I wish to point out that because of DTCO, intrinsic scaling metrics such as contacted gate pitch and minimum metal pitch no longer reflect the actual logic density of a technology. DTCO is enabled by new process technology features, such as gate contact over active area, single diffusion breaks, thin depopulation, and various self-aligned features. The result is a robust 1.8 times increase in logic density and a healthy 35 to 40% per generation chip size reduction for the same design, even when the less scalable areas of the chip, such as analog and I/O, are included. The contribution of DTCO is expected to continue to grow in the future nodes. TSMC is also looking to new areas to continue innovating. We are seeing promising research in many areas of technology. For example, low-dimensional materials, such as 2D layered materials, have presented plenty of opportunities, both in the front end and in the back end of the line. While low-dimensional materials are new to the semiconductor industry, significant breakthroughs have already been achieved in recent years. For example, we have successfully grown high-quality single-crystal hexagonal boron nitride, on a wafer scale. This work was published in Nature magazine, March 2020. These low-dimensional channel and interfacial materials can be transferred onto arbitrary substrates at low fabrication temperatures, which opens up the avenue for fabricating active logic and memory layers in a 3D manner. Another low-dimensional material, the 1D carbon nanotube, is also a promising candidate for future transistors. A key issue that needs to be resolved for the carbon nanotube channel is a thin gate dielectric that enables short gate length transistors. A paper presented at the IEDM 2 months ago demonstrated a breakthrough in high K gate stack on carbon nanotube channels with equivalent oxide thickness suitable for a 10 nanometer gate length transistor. Many more novel materials will be introduced into transistor manufacturing following the long-established trend that started from the use of copper, silicon germanium, hafnium oxide, and various material as gate electrode. The use of new material is not limited to front-end of the line devices. We have already seen encouraging results on the use of cobalt and ruthenium in the back end of the line. We have looked at some examples on how to advance transistor technology at chip level. Advancing transistor technology not only provides performance and energy efficiency gains, but it also provides the necessary headroom to add features and to innovate in architecture and applications software. It is worth noting that without device density improvements, there would be insufficient on-chip cache, no energy-efficient multi-core chips, and since they require more transistors to implement, and no accelerators for the same reason. Domain-specific architectures for GPUs and application processors require additional transistors to perform the specialized functions. Today, the most advanced GPU products have more than 50 billion transistors at chip level and have phenomenal performance and energy efficiency. At the system level, multiple solutions such as TSMC's InFO, CoWoS, SOIC technologies have opened up ways to grow transistor count for the packaged system to over 300 billion. I don't intend to go into the details of how each of these TSMC 3D fabrics technologies work. What I would like to point out is that our industry has already begun to look at beyond just engineering individual chips and have moved to integrate individual chips into systems. Those chips are also called chiplets. Recently, chiplets have become a very hot topic, but some of the industry's pioneer system integration technologies were doing chiplet integration before chiplets were cool. Take, for example, the CoWoS technology. It has been in volume production since 2011, produced more than 90 products with logic dies integrated with memory dies, as well as logic dies integrated with logic dies to boost performance for the packaged system. System on a chip, also known as SoC, is no longer the only optimal system. Systems with several chips packaged together will play an increasing important role. These chips can be specialized in their functions and optimized to improve performance, energy efficiency, density, cost, and functionality. This can be conceptualized as domain-specific technology approach. Domain-specific technologies allowed us to optimize technology according to application and to provide the right level of performance at the right cost for a packaged system. Recent advances in system integration technology, such as 3D fabrics, have made it economical to partition a system into domain-specific technology and integrated chips heterogeneously together. Going forward, we can integrate many more dies in a package. Shown here is an example of integrating 12 active chips onto an active base chip through the use of low-temperature bonding. The total thickness is less than 600 microns. On the right side is the X-ray image of the 12 high stacked die, clearly showing the metal bond and via. Silicon and oxide become invisible in X-ray. Look at that perfect alignment. Here, increasing the I/O count between chips is key to increase peak bandwidth and reducing transistor energy. Today's computing systems suffer from bandwidth deficit. Recent data show that the peak bandwidth grows at about 1.6 times on a 2-year cadence, while the peak throughput growth rate is about 1.8 times for logic. Clearly, there is a bandwidth deficit that limits the system throughput for a broader set of tasks. To increase bandwidth and bandwidth per watt, the most effective knob is to increase I/O count. Fortunately, there is a lot of room for the I/O count for interconnect density to grow, as we will discuss on the next slide. During the past 10 years, interconnect density among chips has seen rapid advances. Chip-to-chip connection density has the potential to improve by another 4 orders of magnitude using SOIC and its future extensions, including monolithic 3D integration. System integration in a package is emerging as a complementary system-level booster to transistor count, performance, and energy efficiency. The progress to materialize the potential for greater I/O density paved the way for us to go beyond just engineering individual chips and move to effectively integrate individual chips into systems. We need more transistors, more memory on chip, and more interconnections between the transistors and the memory, optimized across the system stack from end to end for high energy efficiency. Here, we are just showing a few examples of many possible ways, ranging from packaging to monolithic 3D integration to achieve that. And we will see these technologies increasingly blending into one another. On-chip memory can also enable compute in memory, a new way to perform computation. Regardless of the difference in various technology approaches, one thing is common across the board. That is, energy efficiency is our most important goal in computing. Computation energy efficiency is gated by CV² consideration, which is quite fundamental. Device technologies that minimize the C and use the lowest possible V are needed. Along with improving energy efficiency, we also need to address heat dissipation. Thermal solutions must be developed for future highly and densely integrated chips. All in all, over the past 15 years, our industry has delivered new levels of performance, more energy-efficient computing, achieving about 2 times energy-efficient performance improvement every 2 years. This trend includes the latest 5nm technology that is now in mass production, and our 3nm development is on track to deliver the same level of advancement. System performance and energy efficiency will continue to advance at historical rate, driven by innovations from a multitude of sources, including materials, device and integration technology, circuit design, system architecture design. As our industry and the broader academic research community continue to work together, we will develop technologies that will carry this trend well into the future. A new technology offering on an every 2-year cadence will continue to provide the foundation of new product launches. To bring this to fruition, we need a partnership of all players across the entire industry, from materials and tool suppliers to device technology providers, circuit designers, and the system architects, to ecosystem partners, as well as the broader academic research community. History has shown that most technologies began in the hands of very few and ended up in the hands of many. Along the way, some technologies transformed the world, with society reaping great benefits. For this audience of circuit designers and architects, with the most advanced semiconductor technology now available to all of you, you can really go off and have some serious fun innovating. It is extremely important to foster a broad design ecosystem that lower the barrier to entry and unleash an enormous amount of hardware innovation. Ideally, it should be as easy to innovate in hardware as it is to write software codes. When that happens, we will see another renaissance in application and system design. We are just getting started. Thank you.